Hi, in this video, we want to take a look at classical test theory. Specifically, we want to take a look at generalizability and reliability. Okay, so reliability is the most common way to measure that is Cronbach's alpha. Now, Cronbach's alpha doesn't have a very complicated error structure in its model. So if you look at it for a bit, you might go, you know what? Maybe I want to account for measurement error, standard error, errors in the system in a little bit more complicated manner. Well, right now we're going to take a look at making things a little bit more general and looking at ways to expand what we've got going on for the error aspect. Okay, so this is an example that's modified from Modern Psychometrics with R. Here's the website of the code. And so the big idea here is that we want to extend the reliability measurements to handle multiple sources of error. Specifically, there could be a source of error could be from the student taking the test, or it could be from the question being written in an ambiguous manner. So we want to account for things like this. All right, so for this example, we're going to load the data. Oh, I go ahead and set options digits to 2 just so that we don't get blasted in the face by numbers. We're going to take the R motivation data set from the Modern Psychometrics with R package. And we're going to look at the hybrid columns only. And the reason why we're just reducing down the columns is just to make this a little bit more compact. So as we work through the example, we're just focused on something a little bit smaller. Since this isn't a real analysis, we're just doing this to get an idea of how this analysis works. All right, so then something we're going to do for this one, we're going to say that we have 2 sources of error. With Cronbach's alpha, we basically assume that there's one aspect to error, and there's one error term in the equation. Here we're going to say that the subjects and the questions can be sources of error for us. And so how am I going to denote subjects in this data set? Well, each subject corresponds to one row of the data. So I'm going to go ahead and just make a categorical vector, a factor, of 1 to the number of rows. And so rows correspond to the subject. Now, if you look at this, you'll notice that there's missing values in the data set. So I'm just going to go ahead and use NA omit to get rid of missing values. And now to do this, to do the error structure that I want for this, I need to have question and score be main effects in an ANOVA analysis. Well, to do that, I need to reshape this data, because here, what we've got is each column corresponds to a question. Well, that's wide format. What I want to do is I want to be able to have the subject and the question as like predictors variables in the structure. So I need to convert this to long format. Well, to do that, I'm going to use the gather function in the tidyr package. So here, I'm taking all those columns, and over here I've got the subject. I'm going to reshape it so that I have one column for which question is being asked, and another column for the score. So no information is being lost. And this is redundant. I don't need this. I could just omit this line since I already omitted anything with a missing value. All right, so what I'm going to do, I'm going to run ANOVA with subject and question as main effects. So here, subject and question are the main effects, and the target variable is their score of a 0 or 1. And I have my data in long format. All right, let's take a look at our analysis of variance. And we can just see that we have our sums of squares or degrees of freedom, and with respect to subject, question, and residuals. Now, our residual standard error is about 0.4. Well, it's kind of large, right? I mean, the range is from if the range is going from 0 to 1, that's kind of a large standard error, but oh well, so it is what it is. All right, so now let's go ahead and look at the ANOVA table. So I can see that for subjects, we had 777 subjects. We had 19 questions. Remember, it's always degrees of freedom is n-1. And here's the residuals. And we have our mean squared, or mean squared error coming here. And so the ratio gives us our F value, and from the F distribution, we get our P values. Okay, so subject and question are statistically significant. Okay. Well, let's see if we can look a little bit deeper into this. Can I pull out Cronbach's alpha, or approximately Cronbach's alpha, from the ANOVA table? Yes, I can. What I can do, I can take the values up here and get I can compute Cronbach's alpha. So if I take this value, I subtract off this one, and then I divide by this, I'll get Cronbach's alpha. And so this code here executes that. So at this point, we don't use the degrees of freedom. That's going to be used later in the video. But if I take this code and this, I'm going to be able to compute Cronbach's alpha. So that's nice for us. Now, the reason why I'm able to do this so easily is because this is a Cronbach's alpha has a relatively simple error structure, and so do we. And we still have a simple error structure going on. Now let's take a look at intraclass correlation coefficient. Okay, so the intraclass correlation coefficient evaluates the reliability of questions. So, but a little bit more specifically, it looks to see how much do questions resemble each other. Okay, so if they resemble each other, that looks like I'm running a test on just one subject. Imagine the situation where I would have a test that had math, English, social studies, PE, science, every subject you could imagine, and they're all just thrown in there together. Well, then I would expect to see a low intraclass correlation. But if I only give an exam, let's say on quadratic polynomials, then all the topics are going to be relatively close to each other, and therefore I would expect a larger correlation between the questions. Okay, so let's go ahead and do that. So in the psych package, it's ICC for intraclass correlation. Now I don't want, so when the data I pass in needs to be the score data, and it's in wide format. So this is not the long format that we used previously. And here we can look at our intraclass correlation. And so here we can see it gives the type. Here's the actual intraclass correlation. So we can see average fixed rater is the largest, and you'll notice it's 0.82 again. It's not a coincidence. And then average random raters, and then average raters absolute. And then we get much lower values for single fixed raters and then single random raters. And here is the F statistic, our degrees of freedom. Hey, that came up earlier, right? Degrees of freedom 2. If I look, how does that compare to what we have for residuals up here on degrees of freedom? 13968. 13968. It's not a coincidence. And here we get our p-values. Okay, so let's see. It's, super small statistically significant, super small statistically significant, and the rest are practically 0. So, all right, there's something going on. But wait, there's more, in that we get a lower bound and upper bound on our intraclass correlations. All right, so let's go ahead and estimate the standard deviation from subjects. Now, normally we would probably want to do the we would do the variance estimate, but in a moment, I'm going to show a better way to extract this value. So I'm doing standard deviations. So here, if I take the same numerator we had previously, and then divide by the number of observations for, let's see, the questions for questions, then I can get the estimated standard, or estimated variance, estimated standard deviation coming from the subjects. Now, when I want the estimated standard deviation for questions, I divide by the number of subjects. So here I'm dividing by the number of questions. Here I'm dividing by the number of subjects. And realize since it's degrees of freedom, it has an n-1 aspect, I have to put a +1 on here. All right, well, there's a better way to get these numbers. I mean, it's nice that we can get these values off of ANOVA table, but the smart way to do it is just let the computer do the whole thing and not have to mess around with computations. All right, so if I take the LME4 package and get its, this is a big function in that package, and I go ahead and do a random effects model. Here I can get the standard deviations, and you'll notice it's the same values I had a moment ago. So I have previously 0.19, I get 0.19. Here I get 0.2, and for questions I get 0.2. All right, so looking pretty good. All right, now what we want to look at this point is the generalizability statistics for the test. All right, so generalizability studies estimate variance components attributable to objects of measurements and faucets. So here, basically, for our purpose, these are sources of variance in our data. To get this, we're going to use the G-theory package, and we're going to use the G-study package, and we're going to use the same notation that we used a moment ago with the LME4 package. And so here, when I run this code, I can get estimates of variance components. So by subject, question, and residual. So we can see residual is about twice as big as these two put together. Might be important to know. Now, the next thing I want to take a look at is a decision study. So decision studies calculate the generalizability and dependability coefficients from the variance components. It also provides standard errors for the measurements and estimation. So this is very similar to the G study from like the code point of view. Once again, I'm using the G theory package. Now, instead of doing G study, I do D study because it's a decision study. And here I have to specify what are the subjects on, the subject level analysis of it, and it's going to be subject, and what is the score column, and then we run it, and we get a good amount of stuff out back. Oh, and something I need to point out, we are passing the results from the G study into the function. And this is very similar to what we saw a moment ago, but these are different values. If I look here, I have 0.037, 0.037, after rounding, 0.04. Now we have 0.002. And we have 0.15. Here we have 0.008. All right, so it's a very different, variance estimates. And here we can get an idea of what, here I didn't talk about, with the percent of, what percent does each source of measurement error come into play. And so we can see that here, subject is the big one, but that's also coming from the fact of how I designed the study. Then after that, it's the residual, which is kind of like unaccounted for variability, and then question. Universal variance is 0.04. Generalizability is 0.82. Hey, we've seen that number before. That's not a coincidence. The variance of relative error. All right. And if I want to just grab off one item if I just want the generalizability, then I can just do the generalizability component of the D-study object. And we see it's 0.82. And that's because of the structure that we have here. It's so close to what we have for Cronbach's alpha. Well, that's all I've got for you. Take care and goodbye.